Hello, and welcome back to our plasma survey course. With lecture 19, we'll keep talking about waves. And if you remember where we left with lecture 18, we're going to look at the homogeneous solution for Maxwell's equations, which are going to be our governing equations for our wave. In particular, what we're going to do is take Faraday's and Ampere's laws. Okay, well, let me. Okay. We take those two equations, then eliminate either E or B. Where these are vectors. Oops. I don't know what it was. And then we're going to the last step is going to be to solve for either the wave numbers as function of the frequency or vice versa. And step 2, which I distractedly forgot to write, is to take the Fourier transform. Okay, that's how this goes. And it's all relatively simple, I believe, but let's make sure. Then first thing I'm going to write are directly the Fourier transforms of those the two equations, Faraday's and Ampere's laws. Remember, I'm looking at the homogeneous solution, therefore I'm setting the external currents to 0. And if I do that, I will obtain the equations IK cross E, where E is the Fourier transform. E is equal to minus I omega times B, again, Fourier transform. And the other equation is IK cross B equal to minus, well, let me write it this way, minus I omega over C squared kappa dot, or capital K dot E. The, well, one easy thing to do is to eliminate B. The way you do it is to take B from here. Technical problems. So for B, and then replace in the next equation. I could also solve for E. If I wanted to do that, I will just have to do a little bit of work to figure out how to extract E. It's not all that hard. I mean, you can just take formally the inverse of the matrix K and then multiply back by K once I've got everything sorted out. But solving for B is the more direct way to do it. And that's what actually our textbook does. Not surprisingly, that's what we're going to do. So you find that B sub F is equal to, let's see, I and I cancel out. So all I'm left with is 1 over omega. Wave number K, wave, blue pen, K cross E F. I replace it in the next equation. And I get I over omega K cross E is equal to minus omega over C square bk dot E. Making progress, we only have one unknown left. That did not go well. Why is this thing acting up so much? I don't know what's going on with my pen. Better. Okay, so get rid of the I, multiply over by omega, take everything on the left-hand side, and we obtain that K cross E plus omega square over C square K dot E is equal to 0. And that's our general dispersion relation. You can also write this, square it first. Maybe let me clean it up first. You can also rewrite the same equation using the index of refraction. I would say, well, it of course, it always depends on who's writing, but most people are going to be using K and omega, not the index of refraction, at least in my experience. But the two expressions are equivalent. So if I do that, the advantage, is that I end up with a kind of cleaner, so to speak, expression. N cross E plus K dot E equals 0. That's the other way to write the same equation. And in either form, I need to solve this equation for non-zero E, and that I can only do if the determinant of the coefficients is 0. That is my dispersion relation proper is the determinant of coefficients. Once I have solved that equation, I can, that is, I found the eigenvalue of my problem. I can look for the eigenvectors of the problem, and that's going to give me the first place the electric field, because that's what I used for writing the wave equation. And then from the electric field, I can go back and substitute in the equation for the magnetic field and also solve for that. So far, this is all pretty general, as long as the system is homogeneous. Now, there are things that I left possibly a little fuzzy that hopefully you're familiar with. And hopefully that will be clarified if we look at a specific case. Let's try to do that. This is actually the simplest example. It's kind of, I don't know, not that exciting. Where are we going to find this type of plasma? Well, gotta start somewhere. So let's start from the easiest case and we'll build on that. The simplest case is called unmagnetized plasma. So that's what we're going to look at first. And that immediately tells me something, that I need to be careful about. What did I mean by magnetic field and electric field here? I'm saying now I'm going to look at an unmagnetized plasma. Does it mean that B is 0? Actually, no. That means that the equilibrium B is 0. So the way waves work is something you're very familiar with. When we speak, until we start speaking, there is no sound wave that transmits our voice. When we do start speaking, then those sound waves appear and whatever we're saying gets transmitted. And the act of starting to speak is a perturbation of the initial situation. Like here, I'm assuming that in the initial situation, there is no magnetic field. Then I'm going to do a perturbation that is going to create a magnetic field. What I'm going to assume again is that my wave is linear. And that's all we're going to see in this course. Now, you hopefully will remember and be clear on what do we mean by a linear wave. What I mean is that I'm going to take Maxwell's equations. I'm going to put in a perturbation, and I'm going to solve the linearized version of those equations. We've already worked with orderings in other places in this course. What the linearized equations are the equations where we ignore products of perturbed quantities. That is, quantities that would be of second order with respect to the first order perturbation that we're inserting into the equilibrium. Those terms are going to be assumed to be small, and therefore we'll just drop them. And that is a rigorous mathematical approach. It's not, plasma physicists messing about with because they don't know math. This is the process of taking the limit of infinitesimally small perturbations. And then the proper limit is obtained by keeping the lowest order terms. That's what we're doing. Now, one thing I've not said yet is what do I mean by cold? And our textbook says the plasma is cold. We set the velocities, the equilibrium velocity is equal to 0. That is not quite it. In practice, what we're doing is ignoring the plasma response. Let me be very careful about how I say this. There's nothing wrong in what is stated in the textbook, but that may not be the easiest way to understand what we're actually doing for everybody. Another way to interpret or to understand the assumption of cold plasma will be to state the following. And let's see how confusing it is going to be. I'm going to set the gradient of the pressure equal to 0. This is not quite the same, but I'm going to say, well, if the temperature of the plasma is 0, I get a cold plasma. It makes sense. 0 temperature, like 0 Kelvin, not 0 Celsius or Fahrenheit. And therefore, nothing is moving, and therefore I don't have a plasma. So what am I doing? What I'm doing is to neglect the thermal motion of the plasma with respect to anything else that enters my equations. So that's the idea. And the way I can technically do that is to set the pressure gradient equal to 0. But where there is no pressure in Maxwell's equations. So what is happening may not be all that clear. So what is happening is that if I solve fluid equations for my waves, I'm going to find the same answer. The way the wave is a wave is behaving is to move the plasma, and therefore I need to solve fluid equation for the plasma, and the plasma is feeding back into the electric and magnetic fields. And I need to solve all of those self-consistently and at the same time. What we're doing here is kind of taking a shortcut. I know that if I do it this way, I'm not going to have to worry about what the plasma actually does. And that turns out that works. But we'll get back to that in a moment. Well, a little more than a moment. Okay. End of digression. Let's get back to our system. Well, next source of confusion. We're going to assume that for each species, the density, the subscript S stands for species, is going to be equal to the equilibrium density, which I mark with 0, plus the perturbed density, where N is not the index of refraction, but the number density of the particles. The curse of having so few letters in the alphabet and using the same letters for different things. That may be one of the reasons why most people, including me, prefer to work with frequencies and wave numbers, so I don't have to mix two different ends that mean completely different things. Okay, that was easy. Then for each species, each particle, I'm going to have that the velocity is going to be just the perturbed velocity. Again, I'm assuming that there is no motion at equilibrium. If there is no motion at equilibrium, I cannot have a current. If I cannot have a current, I don't have an electric field. Therefore, the electric field is just the perturbed electric field, E1. And as for the magnetic field, I said my system is unmagnetized. Therefore, the magnetic field is just going to be the perturbed magnetic field. Also, for quasi-neutrality, we need, we need the total charge to be 0 everywhere. So that is the sum over the species of, what does the book use, Q or E? Sorry, E. E sub S, that's the species charge, times N sub S must be equal to 0. That's the net charge in as a function of position. Again, let me spell it out. This is the species charge. Okay, so far so good. Then the way to proceed is what kind of mentioned already. We solve for the current, assuming that the electric field is known, which in practice means we're writing the current as a function of the electric field. And then we replace that current into our Maxwell's equations and proceed from there. The way we do that is to look at the equation of motion for a particle. That's, remember, the microscopic version of Maxwell's equations. We're looking at single particle motion, and that gives me that mass times derivative of the velocity, which is a quantity of order 1 with respect to time, is going to be equal to the charge of the particle times E cross B, E plus V cross B, E1 plus V. Well, I can just replace V1, Vs1 cross B1 in this case. This is just going to be equal to E times E sub S times capital E. And the reason, I'm sure you can see that, is that this term is second order. And therefore, by our earlier assumptions, is negligible. Just wondering now if maybe more need to write that this is what this is. That's for any particle, singular or plural as you prefer. And then I'm going to write an equation for the current, which is pretty much the definition of the current. That's going to be J equal to the sum over the species of N S V S. Then I look up here and find the expressions. Oh, I could have been a little less messy and put vector signs there. Sorry about that. Okay, that's going to be ns0 plus ns1 times v sub s1, which is the only term I have. And again, you see that this piece can be dropped because it's going to give me a second order contribution. Okay, then what we're left with is the linearized system of equations with the correct spelling for a particle. And that's going to look like this. Okay, here maybe another slightly delicate step. Well, let's do this one. dv dt, and I'm going to claim this is actually the partial derivative of v. And remember how we learned of the relation between Eulerian and Lagrangian expressions. So that total derivative is a Lagrangian derivative, which we need to turn into the Eulerian form, and that will have a term v dot grad v, but that's a second order term. Therefore, all we have left is the linear term, which is the partial derivative of v1 with respect to time. Okay, and this is equal to E sub s times E1. And we're going to then follow the book and drop the ones in a moment. I'm going to keep them for one more step. And the current is the sum over S of wow, okay, I'm missing a charge here. Sorry about that. So I have the particle charge, the zero order, zeroth order density, and the first order velocity. So that's again a linear term, and therefore this is J1. Okay, and that's that I'm going to drop from now on. I'm going to drop the subscript 1, but I'm going to keep the subscript 0. The reason being that if I do that, I'm not going to have any doubt about what's an equilibrium quantity. Well, we really have only one equilibrium quantity, so in this case, it's kind of trivial. But what is an equilibrium quantity and what is a perturbed quantity? If I have a subscript 0, that's an equilibrium quantity. If I don't have a subscript, that's a perturbed quantity. Very simple to tell them apart. And sorry, just occurred to me that I don't believe I emphasized this part. In the equation of motion for the particle, there is, well, we're doing it with particles. We could do this with a fluid, but if we did it with a fluid, we will still not have the pressure term. Well, there is no pressure force, regardless of how we sort this out. The reason why there isn't is because we're assuming that the plasma is cold. Okay, so that's kind of the equation of motion of the fluid element is where that assumption affects our calculation. Now, let's get back to the calculation itself. And of course, the next thing we're going to do is what we've been doing. We're going to take the Fourier transform of these two equations. Somehow, what's happening? Okay. Well, for some reason, my writing did not appear on the screen. Okay, now we have it. And what we have is partial derivative. So minus I omega ms vs. And this is going to be the Fourier transform is going to be equal to E sub s E Fourier transform. That's the first equation. And the second one tells me that the Fourier transform of the current density is going to be equal to the sum over the species of E sub s and S0 V sub s Fourier transform. And then we obtain the velocity from the first one. And that's easy to do. Fourier transform. And then we're going to replace it in the second one. Vs sub f is going to be equal to minus E sub s over I omega E f. And then we replace it in the second equation. That gives us the Fourier transform of the current as sum over s of ns0 E sub s square over minus I omega, and I lost the mass here. Sorry about that. Let's see if I can make this work. Let's fix it. Okay. All right. I should have all the pieces now times E. And you'll immediately recognize that this equation is in the form of JF is equal to sigma times E sub F, where the form of sigma now it's very, very simple. That's going to be just the identity matrix times the sum over the species of the quantity I have up here, and S0 E sub S square over minus I omega ms. And you will notice that this expression is kind of familiar, and as 0 is a base square over ms, that's related to the plasma frequency. It's not quite the plasma frequency, but it's close enough that we can use the plasma frequency. Okay. Omega plasma sub s square is equal to n s0 e sub s square over epsilon 0 ms. So we may be on the right track. And in fact, let's rewind a little bit. Here, that's the equation, the first one, the one on top. That's the equation we want to write. So we're trying to sort out an expression for capital K. And that we said in the last lecture can be obtained easily from capital sigma, which I should probably square, as the identity matrix minus 1 over I omega epsilon 0 times sigma. That implies that in our case, K, capital K is equal to I minus, since I have the expression, I just need to replace it there. The expression for sigma is another I, so I collect the I, and I get 1. Then the epsilon naught gives me the plasma frequency squared. That's what I was looking for. And then I have I times I gives me the -1, gets rid of the minus sign. I still have a minus sign in front. Work it out more slowly if you're not convinced. But all that's going to give me is omega plasma square. Oops. I should define the symbol. I'll do it in a second. Let me just do it here. Omega plasma square is the sum over S of omega plasma S square. That's coming from the summation over the species that I have in the expression for sigma that I am now going to square. So we've made amazing progress. We now have an expression for K. Let me look up again. That's all we needed. You can see that, hopefully. And multiplying over by c squared, just not to have too many denominators. I'm going to obtain that c squared times k lowercase k cross k cross e plus taking this to the left-hand side as we did before omega square minus omega plasma square times E is equal to 0. Now that's general. The next thing I can do is to define K, or equivalently, I can define my frame of reference. That is, so far I've not said anything about which way the axes are pointing. The reason why I've not done it is that it doesn't matter. There is no preferential direction. But now I do have a preferential direction. That's the direction of the wave vector K. And therefore, I need to solve this equation by components. I need to specify a set of coordinates in which I can write down K. And then we're going to do it in the simplest way. What I'm going to do is take the z-axis to be parallel to the k vector. In other words, my k vector is going to be equal to 0, 0, k. And this is completely general. I'm simply taking advantage of my freedom to select the axis and setting them up so that k is in the z direction. I could make a different choice. I could make it in the x direction. I could say, well, it's going to have an x and y component. At the end, I will get the same result, just transform in a different set of coordinates. So this is the easiest, the cleanest way to do it, which is still going to look a bit of a mess, because the electric field in general is still going to have 3 components. There is nothing telling me that any one of those components should be automatically 0 if I define k that way. Then what you do is use the plasma formulary or something else to, or just know it, to remind yourself of what this product is. K cross K cross E sub F is in the form A cross B cross C, which we know to be equal to A dot C times B minus A dot B times C. And let's see. That's going to give me K times E Z times K, which I'm going to write as K Z hat. That's A dot C, and minus A dot B minus K squared E, and that gives me K squared EZ Z direction minus K squared times EX, oops, these are Fourier transforms. But so easy Fourier transform the Z piece. And here I have the also the X and Y. And you see that these two are equal and opposite and cancel out. And therefore, what I have at the end is minus, there was a C square here in the equation on top, so it's minus C squared K squared, and then that term sums to the omega square minus omega plasma square, but only for the X and Y component, not for the Z component. So in matrix form, my equation is going to look like this: minus C square K square plus omega square minus omega plasma square, 0 and 0. For the Y component, I have 0, the same term, minus C square K square plus omega square minus omega plasma square, and 0 here. Then I have 0 and 0, and only omega square minus omega plasma square. And this multiplies my EX, EY, EZ, and the product must be 0. 0 vector, of course. So that's going to be possible for a non-zero electric field only if the determinant of the matrix is 0, and that's what we're going to do next, is write down the determinant. Minus, I'm just going to write it the way it's more familiar to me. So it's going to be K squared C squared instead of the other way around. Plus omega square minus omega plasma square all square times omega square minus omega plasma square must be equal to 0. Then I have essentially two options. Either omega square is equal to K squared C squared plus omega plasma square. And in that case, the Z component of the field will need to be 0. Now, I'm still writing the Fourier transforms, but of course, if I transform back into physical space, if the Z component of the Fourier transform is 0, that means that the physical component, the physical Z component of the electric field is also going to be 0. Let me be explicit. So that's option 1. Option 2 is that the second term in this product is 0, that is omega square is equal to omega plasma square. In that case, Ex and Ey must be 0. So those are my two general solutions for this system. Okay, now what is really happening? So I've decided that my wave is moving in the z direction. That's how I pick the z direction. Look at which way is the wave going. Set that direction to be the z direction. And now I find that there are two possible families of waves that in which the propagation, the direction of propagation of the wave is the same, but the electric field is in different directions. In fact, what we have is in the first case, where the electric field has an x and y components, that is called the transverse mode. Transverse, whichever. And the other one is called the longitudinal mode. See if I can make this fit a little bit better. And you'll notice that, let me call these 1 and 2. In the first case, K dot E is equal to 0, because we said E does not have a Z component, K is in the Z direction. And E is equal to EX, EY. Sorry, EX is not a vector. It's a component, and 0. Oops. While in the second case, we have the K cross E is 0 because they're parallel, and the electric field is given by just its Z component. We did this pretty slowly, but that's how you do things in general. Now, this is probably a good place to take a break. What we're going to do in the next lecture is briefly discuss both the transverse and longitudinal modes. And then we'll look at the case with the magnetic field. That's already going to be a little bit more cumbersome. It's not that much more difficult, but there is going to be more symbols to keep track of. So we'll have to be a little more careful about how much space we need and how we use it. Okay, that's all for today, and I will see you back for lecture 20. Thank you.